Hey y'all, welcome back. Today's homework is all about inverse functions. So let's work some problems. Suppose f of x is a polynomial function containing the points in the table below, and you can see the table. We've got our inputs on top and our outputs on the bottom. These values in the first row are all possible values for x, and then their corresponding outputs, or their f of x values, or y values, if you will, are listed below here. And it says use the table to evaluate these different expressions. So number one says f of 3. What you need to know here is that f of 3 is telling you to find the value when x is 3, the value of the function. So in other words, it's telling you to look at the table and report back the number in the f of x row when x is 3. So we see x is 3, f of 3 is -1. This also represents a coordinate pair, a point that you could find on the graph of f of x. It would be 3, -1. That point would be on the graph of the function, and this xy coordinate pair would satisfy the function. Number 2 says f of 1. Again, we're going to look at our x row, and we see x is 1 here. And so we want to report back what is f of 1. F of 1 is 5. Number 3 says, what's f of 5? We're going to find 5 in the x row, and f of 5 is 0. So again, they're just asking for this particular point, 5 comma what? 5 comma 0. F of 5 is 0. Now for 4, 5, and 6, the question is reversed. It's asking for you to find the inverse of f when the value of f is 3. So it's a kind of a weird way of saying, hey, instead of looking for the x value, like we did up here, we found where x was 3, y was -1. Here it's saying, when y is 3, what's x? So one way to think about this is that, for instance, if we look at number 1, this number right here is x. And this number is f of x, or just to make it a little easier to think about, it's y. The really sloppy y there. Let's see if I can make that look a little nicer. X, y. For number 4, for these inverses, remember that the domain and range are just reversed for these inverses. So the input here is going to be the y, and the output is going to be x. So what this is saying is find 3 in the second row and report back what x value would correspond to that. So in this case, the inverse of f when f of x is 3 is 6. Another way to say it would be the x value is 6 when if f of x is 3. F inverse of 5. So again, they're giving us the y value here. We're going to look for 5 in this second row. It's right here. And we're going to report back the x value. So if the y value is 5, x value is 1. For number 6, we're looking for where f of x equals 0, and we're going to report back what the x value is. So f of x equals 0 right here, also right here. Interesting. So this means that the inverse of f is not a function, because the f inverse, when there are 2 points, in other words, where if our input is 0, we get 2 different outputs. See, we have it right here and right here. So that means that this is going to have two outputs and equal one of two things, either equal 0 or 5. This is why the inverse cannot be a function. By definition, looking really bad over here. By definition, a function can only have one output for any given input. So while you still can have an inverse that's a relation, it's not going to be a function. Okay, so we're going to say it's either going to equal 0 or 5. Got to get a little space in there. Here's what we'll do. Okay, number 7 says, is f a function? Well, we just talked about the fact that the inverse is not a function, but let's verify whether or not f was a function to begin with. Notice that there are no inputs that give two different outputs. Each input, 0, 1, 2, 3, 4, 5, 6, is only mapped to a single number. 0 goes to 0, 1 goes to 5, 2 goes to 2, so on. So in the relationship where x is the input, we do have a functional relationship. So we would say something along the lines of yes, and to explain how we know that, each input, I'll say, corresponds to exactly one output. Is the inverse a function? Okay, well, we were just talking about that. We know that the inverse is not a function. No. 0 corresponds to different outputs. I think that's really the only violation here, right? All the other, I don't see any other repeated values in this row that go to two different numbers. So I think it's just 0 that's preventing this from being a function. In other words, if we were to graph this inverse function, it would fail the vertical line test when x is 0. Okay, let's take a look at this graph. Let's see if we can't make sense of what's going on here. Got a graph, no numbers or anything. It just looks like maybe it's it's kind of like maybe half of a sideways parabola maybe, or maybe it's part of a ellipse. I don't know. We don't really know what it is, but we should be able to answer these questions. Does f of 0 equal? Okay, so just to be clear, this graph is f. Okay, so all of the y values are all the y values are what we're going to put for number 9. Not all the y values, sorry, just a y value. X is going to be this horizontal axis. And so there's really two key points we want to look at here. We want to look at the y-intercept right here. And the x-intercept, which is here. Let's name these 2 points. One is 0, comma, well, b, not 6. We don't know what the number is. Just know it's b. And this point over here, this x-intercept, is a, comma, 0. So if this first question, number 9, is asking what's f of 0, well, when x is 0, the y value is b. Our answer is just b here. Number 10 says f of what is 0? So f of what x value outputs 0? Well, that's going to be here, it's a. F of a is 0. For number 11, says the inverse of f at 0 is what? So remember, if it's just the normal function, input is the x and the output is the y. Talked about that in the last section. When you start talking about the inverses, you're going to swap the x and y. So here we're looking for the y value, b0, and it's asking which x value corresponds to that y value of 0. So looking at these 2 points, we can see that when the y is 0, the x is a. F inverse of 0 is a. Number 12 says f inverse of what is 0? So f inverse of which y value corresponds to an x value that's 0. And that's the y-intercept over here. When the x is 0, the y is b. Number 13 says the domain and range of a function f is 5 to infinity, and its range is -2 to infinity. State the domain and range of the inverse of f. Well, there's nothing really to show here. You just have to understand that the domain and range are reversed for the inverse. So the domain of, I'm going to leave a little space so I can type in a f inverse there, is, well, let's actually go ahead and throw that in here. F inverse. The domain of f inverse is going to be the range of the original function f. That's going to be -2 to infinity. All right, the range of the inverse of f is going to be the domain of the original function f. So yeah, it's just backwards. The domain of the original function is the range of its inverse and vice versa. Number 14 says algebraically find the inverse of the following functions. So for each one, we will find its inverse function. So for this first one, we've got y equals 2x plus 3. We'll start by swapping x and y. So x equals 2y plus 3. Now we'll solve for y. Subtract 3 from both sides. And then divide everything by 2. 1 divided by 2 is 1/2. 3 divided by 2 is 3/2. So the inverse of y, this really isn't, kind of interesting that this is not using function notation here. So we don't want to just inject that. I think I'm just going to say inverse of y like this. This is pretty unconventional, but also I think it'll work. The next one, start by swapping x and y. X equals y squared plus 5. Now we'll solve for y. We have x minus 5 equals y squared. Now, at this point, we're kind of done here because we can't isolate y and still be left with a single expression for y. Because when we take the square root of both sides, we're going to end up with a plus or minus here. Anytime you take the square root of both sides of an equation, you have to include the plus or minus. All right, so the inverse here is not going to be a function. I'm going to hesitate to even write it using function notation because it's not a function. I think what I'll do is just call it the inverse of f. I think I'll go ahead and do that. I think that's fair. Not a function, but it is the inverse. Okay, the next one. Start off the same way we started all these, by swapping x and y. Then we're going to add 5 to both sides. Kind of looks like the last one. Now we'll divide both sides by 4. At this point, we're going to have to cube both sides. Fun. It's going to be quite the function here. I'm not actually going to do the algebra to multiply all that out. I'm just going to leave it factored form here. And then we need to subtract 1 from both sides. All right, so not the most elegant equation here, but here is the inverse. Okay. Now, this one is a function, so I do feel comfortable writing it in that form, not using that function notation here. This makes me a little uneasy over here. Okay. And there we go. Let's take a look at number 15. Let's complete the table and graph the function on the interval. So let's go ahead and start with the table. I'm going to substitute in 0, I'm going to get 1. If I substitute 2 into this function, I get 1/4 times 4 would be 1 plus 1 is 2. If I plug in 4 squared 16 times 1/4 is 4 plus 1 is 5. And if I plug in 6 squared is 36. 36 divided by 4 is 9. 9 plus 1 is 10. All right, let's go ahead and plot these points on here. 0, 1. 2, 2. 4, 5. Starting to see this parabola take shape. And 6, 10. We're only graphing it over this interval 0 to 6 here. So it's be a little shaky because I'm using a mouse, but I want to try to connect the dots here as good as you can. Okay, 0 to 6, nothing outside of that. I'm not going any less than that. And actually, this says strictly less than 6. So what I really should have at this x equals 6, we're not going to include that endpoint in the solution set. Really should have an open circle here. Yeah, that. Okay. Number 16 says complete the table for the inverse of f and solve for the equation algebraically. So let's go ahead and do the table here. All we need is going to be to flip this table that we have up here. And what I mean by that is just swap the domain and range here. So I'm going to have 1, 0, 2, 2, 5, 4, and 10, 6. And maybe I'll plot this one in green just to make it look a little different here. All right, now this 1, 0 should be an open circle like we had on inverse. So, or on the original function. So 1, 0. Oh wait, hold up here. No, I take that back. That's going to be the 10, 6 is going to be the open circle. So yeah, here we've got one at 1, 0, 2, 2. Ooh, same point. Check that out. That's nice. 5, 4, and 10, 6. That's going to be the open circle. We should have a perfect reflection of the original function over the line y equals x. I'll do a quick sketch of that just so you can see. The line y equals x is this 45-degree line. Doesn't do that. Let's try that again. It goes basically something like this, right? Now, you can see how the red graph here is the mirror image of the green graph. So we can rest assured that we graph this correctly. Now it says also solve for it algebraically. So to do that, I'm going to swap x and y. I have x equals 1/4 x squared plus 1. I'm sorry, y squared. Now we're going to solve for y. Now because of our domain restriction, we actually are going to get a function here. I'm going to subtract 1 from both sides. Then I'm going to multiply both sides by 4. And finally, I'm going to take the square root. The square root of 4x minus 4 equals y. And typically we would need a plus or minus here because we are taking the square root of both sides. But because of our domain restriction, notice there are no negative x values for our original function. It gets cut off at 0, so there's nothing over here. Similarly, on our green graph, on our inverse, there's nothing below the x-axis. So we don't have any negative y values in the range of the inverse. So we're just going to delete this plus or minus because all of my y values here are positive. Now, since we get to delete that plus or minus, that means that the inverse here is going to be a function. So I will write it like that. F, the inverse of f is the square root of 4x plus 4. And I think if you plug in these numbers, they should all kind of work out. 4 times 1 minus 4, that is 0. 4 times 2 is 8. Minus 4 is 4. Square root of 4, 2. So that checks out also. If I plug in 5, 4 times 5 is 20. Minus 4 is 16. Square root of 16 is 4. And finally, if I plug in 10, I get 4 times 10, that's 40, minus 4 is 36. Square root of 36 is 6. So everything's all good there. The last problem here, we're given the formula for converting Celsius to Fahrenheit. These are 2 degrees that measure the temperature. So in other words, how hot it is in your room or outside, or anywhere, I guess. The first question says, okay, find the inverse of this function. So I want you to keep in mind, this is the F is the Fahrenheit, and here the X is the Celsius. So make a little note here. that the Celsius is F, Fahrenheit is F of X. I'll just call that Y for now. We're going to find the inverse. And we'll start by swapping X and Y. Now to solve for Y, I'm going to start by subtracting 32. And then I guess I'll take this in 2 steps. Could get away with just dividing both sides by 9/5, but I think it might be easier just to first multiply everything by 5. What would that be? 60? Is that right? 5 times 2 is 10. 15 carry the 1. Okay, yeah, that's good. Equals 9y, and then finally divide everything by 9. Yeah, it's going to be 5/9 x minus, does this reduce at all? 160 over 9? Let's see here, 160 over 9. I think it's, that might just be it. Right? Let's see, 3. No, yeah, that's it. Okay, so here's our inverse, right? This is going to be F inverse. Now going back to our discussion about swapping domain and range and the X and Y values here, the next question wants you to explain like what's the purpose or the meaning of this equation we just came up with here. It's not enough to just say that it's the inverse of this function. I want you to think about what this represents. And here's a good way to think about it. The original function has you converting Celsius to Fahrenheit. In other words, if you put in a number into X, your inputs are in Celsius, your outputs are in Fahrenheit. So if you plug any Celsius degree into this equation, it'll output the degree in Fahrenheit. Once we swap those 2 variables, we switch the domain and range. Now our inputs are Fahrenheit and our outputs are Celsius. So basically, we're creating the reverse conversion form, where the original one was converting from Celsius to Fahrenheit. This equation is converting, or I should say, can be used to convert Fahrenheit to Celsius. And you don't have to word it exactly like that. You can kind of put it in your own words, make sense of it yourself. But that's it. And it looks like that's the last problem of tonight's homework. So thanks for watching. Y'all have a great day.